We are going to find the overall heat transfer coefficient and the heat transfer, the Q, for two geometries where air is flowing at atmospheric pressure 300 degree Kelvin and Reynolds number of 50,000, and the surface temperature it remains constant at 100 degrees C. Now these two geometries, one of them is a cylinder with the perimeter of 10 centimeter and length of tube 1 meter. The other one is a flat plate, length of 10 centimeter and width of 1 meter. Now, both of these geometries provide exactly the same surface area to the air. And we're going to see like what would be the difference in terms of the heat transfer for these two cases. So for case A, when we have flow across the cylinder, so let's say this is the cylinder that we have, and flow with the T infinity just passing through that. Perimeter is 10 centimeter. The length of the cylinder is 1 meter here. And Ts we know is at 100 degrees C. Depth constant at 100 degrees C, and the air is flowing at 300 degree Kelvin. So Ts is 373 degree of Kelvin. T infinity is 300 degree of Kelvin. So film temperature is going to be Ts plus T infinity divided by 2, which will give you 336.2 of degree of Kelvin. Now, having that one, we can find out what we need. Prandtl at this TF is going to be 0.702, and conductivity at this film is going to be 0.029 watt per meter Kelvin. If you use Hilbert equation, then Nusselt number D is C Reynolds D to the power of M, Prandtl to the power of 1/3. Now, the Reynolds number is given at 50,000. So at RE 50,000, value of C is going to be 0.25 and M is going to be 0.805. So the Nusselt number of D would be 0.027, 5 times 10 to the power 4 to the power of 0.805, and Prandtl is 0.702 to the power of 1/3. So we are getting 145.5, and it's going to be HD divided by K. Now diameter, we can find it from the perimeter. Diameter of cylinder is pi d, which is 0.1 centimeters. So d is going to be 0.1 divided by pi, 0.315 meter. So having everything here, we can find h, which is 148. I guess this one is 148. 148.5 times 0.029 divided by 38. So the value of h is 133 watt per meter square Kelvin. This is K for the first case, and we can find Q. It's going to be H, the area available to the flow, Ts minus T infinity, and it's going to be 133, 0.1 meter times 1 meter of length, 373 minus 3. So Q is going to be 0.97 kilowatt. That's for the case of cylinder. Now, if we look at plate, which provides exactly the same surface area. So this is the surface area that is provided by cylinder. Now we have a flat plate with the dimension that's given. So Reynolds number, we need to first define whether it's a laminar or turbulent, therefore which is less than the Reynolds number of X, and critical, which is 5 times 10 to power 5. So it's a laminar, and the equation for laminar average Nusselt number is 0.664 Reynolds to the power of half Prandtl to the power of 1/3. And for air at TF, we know all the properties that we need. So the Nusselt number is 0.664, 5 times power 4 to half, and Prandtl is 0.702 to the power of 1/3. This is going to give you 132, which is average HL over K. And from here, the heat transfer coefficient is going to be 132 times 0.29 divided by 0.1, which is 38.3 watt per meter square Kelvin. This is H, and Q is going to be HL. It's consistent here. HL area is minus T infinity. And if you plug in number 38.3 times 0.1 times 1, 373 minus 300. So we are gonna get 0.297 kilowatt. And that's gonna be the rate of heat transfer from a flat plate that provides exactly the same surface area as the cylinder that we investigated.